DuckDB is easy to use, supports single node in-process analytics, and offers easy access to multiple data sources. These are already critical features in building a data lakehouse solution, but the recent release of DuckLake really sealed the deal, with an optimized implementation of features like snapshots, schema evolution, and time travel. Today I'm gonna show you how I integrated DuckDB and DuckLake with dbt to support my own personal data lab, a place where I can ingest and transform datasets to help me further develop my data skills. You probably haven't seen this elsewhere yet, right? Let's have some fun! First, we need a goal. As promised on the last video, this time we were working with music-related datasets, and the goal is to integrate multiple datasets into a knowledge graph that will power a simple music discovery algorithm on top of KùzuDB. This video will show you how to retrieve and prepare the data so that it is ready to import into KùzuDB, and only next time we'll dive into Kuzu. Let's start by looking at our tech stack. And so for our compute engine we are using DuckDB, specifically the Python API, the Python DB API, and we are then using DuckLake as our metadata storage extension for our catalog. We are able to choose different catalog databases. We can use DuckDB, Postgres, SQL or MySQL, and we opted to use SQLite. There are some suggestions on how to do this selection, and if you'd like to perform local data warehousing using multiple local clients, you can use SQLite. If you use DuckDB, you are only able to connect from one single client, and at the very least, if you'd like to connect using your file system database and use a memory database to monitor your inserts or your operations, you could do that if you're using SQLite, while you couldn't do that using DuckDB. So I opted to use SQLite. We're not going into a solution like MySQL or Postgres just because this is a personal data lab, so we're not expected to collaborate with many people, and we are focusing on a single node operation. There are still ways that lets us share our work, but we just don't expect to do it concurrently. So DuckLake supports all the basic stuff that you need for data lakehouse that other formats like Iceberg or Delta Lake already support. So for checking your snapshots, you can just query from your catalog directly using this snapshots function, and this will show you the change log essentially. If you want to select from a particular version, you can do that by adding this after your table. So you can use a numerical version, or you can use a timestamp. It also supports schema evolution as expected, and you can store your actual data outside of DuckDB, DuckLake or SQLite. These will be stored in either your local file system or using an object store. For this example we are using S3, so we are going to install a min.io, and we are going to use that. You certainly can use this in your local file system if it makes more sense to you, but personally I wanted to have something that lives outside of my main laptop. I have a tiny home lab made of another laptop that's running Proxmox, and in there I have a min.io instance, and so I decided to drop that there. And so this brings us to our last component, which is min.io. As I was saying, we are using this for object storage, but we can use AWS S3 or any other compatible S3 API to store our files. Finally, we are using DBT, which is the glue that brings all this together. And DBT has many adapters, and it supports DuckDB as an adapter. So you can save all your secrets, set them via environment variables, and associate them with an output. But more importantly, you can also attach external databases using DuckDB. Unfortunately, for the current version, it doesn't really support the attributes that we needed over here, which would be the data path. But there is a PR that's already closed, and that lets you do this. And what we did was just to install this version, which is code that is at this point unreleased in a stable version. And this seems to work perfectly, no problem there. So this is kind of a preview into what future DuckDB will let you do with DuckLake. So our architecture, they have a post over here, the DuckLake manifesto, and they have this section on scalability where they cover storage, compute, and metadata management as the three main components. And this is essentially what we are doing here. We have storage on S3, compute is handled by DuckDB directly, and metadata management, or our catalog, is handled by DuckLake. Just a small detail about MinIO. It just recently removed several web UI features from the community version. And as you can see, this was the old web UI, which is still available, but probably won't get any further updates. And this is the most recent version. As you can see, pretty much all features except creating a bucket are missing. This is not completely critical if you just want to test it, but it's a shame that stuff like policies is no longer available, because it would let us learn a lot without having to go into S3. Yeah, but it is what it is. So let's quickly look at the storage layout for the S3 Lakehouse bucket. Let's begin by the raw directory, which is the ingest prefix. Each subdirectory will be a dataset that was ingested at a given time. It can be CSV, JSON, Parquet, really any type of file that you like to store, although only a few of these types will be, loadable. Each dated directory structure will have on the top level a manifest JSON that contains the latest path for each dataset. You'll also find a stage directory which just stores Parquet files for DuckLake. The same happens for a marts directory, but it contains one DuckLake catalog per domain, for instance graphs. And finally you have an exports directory which contains exports from one of the data marts, and these exports are again dated, and the manifest again points to the latest version. Everything that you find here that is dated can be pruned using the command line, so you can delete old versions, so you can run an ingestion multiple times and then delete the old versions, or you can run an export multiple times and then just delete the old version. It shouldn't be in use anyway. And finally you have a backups directory which contains a backup for your catalog. This contains the engine or the compute unit which is implemented in DuckDB. and this database will attach to these catalogs, so which are in SQLite, and this is the stage 1 and multiple ones for marts. If you need, you can restore any of these versions, but of course we are not backing up any of the data on the data paths, so it assumes that the data is still available over there if required. At least for the stage and the marts, this should be the case. It won't so much for the raw directory, because this should have already been ingested by the time it reaches the catalog. Also, we have everything is documented here, so you can go through the README to get a nice overview on all the details. This also shows how the generic workflow should work. So you have a data set. It can either be a manual upload, so you are just creating a data directory and uploading files onto that directory, or it can be a Kaggle dataset URL or a Hugging Face dataset URL. This will be ingested into min.io, so it will be essentially just retrieved, downloaded. Then we run the transformation, which is based on DBT and DuckLake again. And finally we can export any of these transformations into plain Apache Parquet without any of the DuckLake logic behind it, and you can use this wherever you want to. And so this is essentially what this package does regarding the Lakehouse sub package. So let's get into our project where we integrate all of this. So we created this data lab project, which should be public by the time the video is released. And in order for you to install this, you just need UV with Python 3.13 installed, and you also need access to an S3 compatible object storage. We are using min.io. We also provide a Docker Compose that with min.io pre-configured that you can easily use if you want to test this out without having to install anything else. Of course, you need Docker to be running for that. And so a quick start is just to copy your .env.example into your .env and replace whatever you want to replace. You can leave it as the default and you use this to log in into min.io. Then you run Docker Compose up. This will set up min.io if you want to use the packaged solution. And then sometimes you need to specify the region and configure a specific one under configuration region in min.io. This is only available in the older version of min.io, not the updated one. And this is the one we are still using here. And so let's jump into the terminal and take a look on how to set this up. So let's do it in a temporary directory. Once you have this installed, you can just go into here and copy the .env example into a .env. You can go into the .env and replace. You should have to replace only this section at most. For this particular example, if you are using the Docker Compose, you can leave this as is, and you can simply change this into, let's change it into admin and admin, something like that. This section lets you customize where the bucket will live. We are using Lakehouse as the root, and then you can customize each prefix for this ingest prefix. This is where our datasets, our raw datasets will live, and the stage prefix is where intermediate data will live. At this stage, this will correspond to a DuckLake catalog, And then we'll have multiple DuckLake catalogs in the individual catalogs for each data mart. For example, we are working towards building data that can be imported into a graph. So we are creating a graphs mart catalog. And then we have an exports directory where we can export one full schema from one of the catalogs into Apache Parquet. And finally we have a backups prefix where we can drop our engine DB backup as well as our catalogs backups. Finally, we have some DuckLake configurations as well as some KùzuDB configurations. These will all live under the local directory and are not committed to Git. So we have an engine DB, which is DuckDB. We have a stage catalog, and we have another catalog called graphs, which is part of our data marts. So this is the gold layer data, it's ready to use. And we also have a graph DB in Kuzu, but this will not be covered in this video. So now let's save this and let's start our min.io instance. And there we go. Let's just check that this is correctly created. Okay, and so admin, there we go. We have one bucket called Lakehouse. So now let's take care of installing the Python dependencies. There we go, and then we can activate the virtual environment. I'm using fish, so this is .fish. You're using bash, just run this script instead. Here we are, and once we are within this environment, we'll have access to DLCTL, which will help you, automatically load the environment variables that you need. We are storing multiple exports within our Lakehouse, so this will also help you automatically identify which export to use, and it defaults to the latest export. And this is done through environment variables that are loaded automatically by DLCTL in the proper moment. So first of all, we are going to look into DLCTL ingest. And as you can see, you can ingest a dataset, list, ingest the datasets, or delete all the old ingestions. So every time you run this command to ingest a dataset, it will store it with a timestamp associated. So you'll always have every version that you ingest unless you delete it. You can use prune to delete all older versions, or you can do it manually depending on whether you are just clearing old stuff or want to maintain old versions manually. So one thing we can do is create a manual data set. So something like this. This will let you, let's for instance create a data set for this Snap Facebook large graph that is available online. Oh yeah, I forgot data set, right? There we go. So it created this directory under our S3 storage, which is under raw, and it's called Snap Facebook large, and it's got this date. It's the only one, so we can't miss it. So if we go into our min.io and refresh this, we'll see a raw directory, Snap Facebook large. This wouldn't be listed unless there were a file inside, so we just create a keep .keep file in order for this directory to be visible. And now we can go into the snap web page and unload this dataset. And here it is. I have just extracted the files from the zip, and this is what we have. We can now upload it into min.io. If we go in here, we can simply drag these files over here. And there we go. We have a new dataset available for us to work with. We'll probably parse these files and ignore the remaining ones, but it's fine that they are here. But we are not going to do this manually. I'm going to show you what other datasets we can load. Going back into the terminal, one dataset that we can ingest is this Kaggle dataset, and let me just copy this. And so by default, ingest dataset will take a URL. If this URL is from Kaggle or Hugging Face, it is able to handle these types of datasets. So let's ingest these are social networks, which we have actually implemented transformations for. So if we go into our object storage and refresh, we'll be able to find these are social networks. The manifest will point to the latest version that we have ingested, and that should be this file. As you can see, it's the only one we uploaded today. And in here you'll find the folder structure for the dataset we just downloaded. Let's download another dataset from Hugging Face just for demoing purposes. And as you can see, it also loaded this dataset in a similar fashion. Let's just, out of curiosity, load it again to see what happens. You run it again, it will still download the dataset, but now it will create a new folder with a different time when it was uploaded. And the manifest will actually point to this file over here. And we can clean old versions simply by running the command dlctl ingest prune. And if we go back to min.io, we'll find a single latest version is available here. The time changed just because I had done a few other runs meanwhile, but this one is the latest one. We can also list these files via command line, so we can ingest ls, and this will show us all of our datasets, only the latest version. Or we can check all versions, which should be the same because we just ran prune. But just out of curiosity, let's run this one again. And let's lsa. As you can see, we have two versions now. And so if we run prune, we should keep the one from 1505. As you can see, this is the one that we kept. Now let's also load, or rather ingest, this dataset, which we are going to integrate as well into our graph. So you can see this one contains a sample of MP3. This is a part of the dataset. We're not going to use the MP3, but it's still here, you know. Now for transformation, you can run the LCTL transform. If we run it without any arguments, it will run all transformations on DBT, but we can run it with the -m for model argument, and in this case we are just running the transformations for these social networks under the stage catalog. On the previous run there was an error due to lack of memory, so I increased the memory for WSL2 and we were able to run it. We'll have to check out why this is happening, because it should run even for lower memory systems. I had to use 24 gigs for WSL, and I believe we can set memory limit on DuckDB and use less memory for this. Either way, we now are going to transform our million song dataset as well. This should be faster. We'll look into why it was so slow for the previous dataset, and it is done quite quickly. We can also run all transformations through this command directly, but instead we are going to run the final transformations for the graphs music taste, which uses the previous two-stage datasets to prepare the data to be loaded into a graph. So I believe this should be enough to run that. So it was actually missing the marts prefix. And here we go. And now if we go into min.io, we'll be able to find a stage directory, and this contains Parquet files generated by DuckLake. We also find a marts directory with the graphs subdirectory, and again this contains a bunch of DuckLake files. So now let's go into VS Code and look at our DBT project specifically, which is under transform. First let's look into the configuration files, and specifically profiles. So our profiles contain a Lakehouse output, which is our default target and the only target. This is a DuckDB type. We fetch our local dir and set it to run within the EngineDB environment variable, which will output into here, engine DuckDB. We install these extensions. We obviously need DuckLake and SQLite. We set up our secrets over here, which are essentially just imports from our environment variables, which already exist. And finally, we attach our catalogs over here. This is only possible because we are using the PR version, so the unreleased version. It should be released quite soon, either way. So now let's look into our DBT project. This is a pretty standard DBT YAML, but in this section we have our two top level namespaces. For the stage namespace we are using the stage database, while for the marts we are using a database per data mart. So for the graphs one we are using graphs. We are using table materialization as our default, we could be using views, but most of the files we are generated should be materialized because it takes a while to run these computations, at least for these social networks. And for the marts, for the graph smart, we need this data to be used directly, so we just materialize it as a table. And we keep separate schemas within stage and marts. So for these social networks, we use the DSN schema, and for this million song data set we use this MSDSL schema. We also changed the way schemas and table names are created by implementing this macro over here. So this lets us use the schemas as they are defined in here. Otherwise, something like main underscore DSN would be used instead. So we want to use exactly what we define here, and this is why we define this generate schema name as well as this generate alias name. And finally, we have some macros that we use for these social networks, just because we have 3 subsets per country and they are loaded exactly the same way. So if you go into load these geners, you just have a macro which gets the S3 path, which will be dependent on the country, and we just use this query to read the JSON, and then we iterate over each key value and cast it to a user ID and an array of varchar which contains the geners. So this is probably why it was taking quite a while, because we are doing what I believe is a cross join, unless there is some special implementation for this JSON-H, and this doesn't work quite well with such a large object. This is why we had to increase the memory. But either way, I'm not sure if there is a way to optimize this for this particular data, or if it only maybe we have to implement a preparation stage in Python where we split the JSON into several separate objects per user and gener array. But that would kind of, defy the purpose of using DuckDB directly. Either way, I don't mind waiting for a while longer if it's just faster to implement and I don't have to think about it and I can do something else in the meantime. So we have a similar macro for edges. It just reads a CSV. This is quite efficient because it's just a regular CSV. There is a node 1 and node 2, so the source and target for the edge, and we just cast it. Then we use this we call these macros under models. So for the stage under these social networks, we have a model for each of these edges and geners tables for 3 languages. So we have Croatian, Hungarian and Romanian. And so this essentially just calls the macro and uses this environment variable that is injected by the LCTL with the path of the latest version for this dataset. For each package over here, there is also a schema, a file. This schema file serves 2 main purposes. It lets you document your models, and it also lets you implement some data tests, which are extremely useful, particularly when you are preparing graph data and want to make sure there isn't a duplicate node ID or stuff like that, or that you don't have an empty list for some reason. This macro list not empty is actually a test that is implemented over here. List not empty, just a query that returns data when the test fails. The same for a positive integer, it checks that if it's null it's already failed, or if it's less than 0 it's already failed, or if it doesn't match, you know, an integer number without any decimal part, then it fails as well. And now let's look into the million song dataset 1. So we have a really large CSV that we load. We can cast the types over here. To save some memory, just use floats and integers because these features are not that relevant for our end goal. There is this part which is particularly interesting, where we transform our tags into, you know, title case array of genres. So these are initially stored as a comma separated string. We just run string split, and then for each tag we transform the tags by replacing the underscores with a space. And meanwhile we convert the first character into uppercase and remaining characters into lowercase. Sadly, there is no DuckDB function for title case, otherwise we wouldn't need to even implement this. At least we would still need to split it, but not implement this part, you know. Then we have the user listening history, which is similar, just it provides a track ID, a user that listened to this track, and how many times that user listened to the track. And this is our intermediate data, so this is already within a DuckLake, a separate catalog for staging. And then we go into Marts, and then we create our music taste graph, which integrates all of this info. So we have DSN nodes for users. We just integrate all users into a single table, and then we create a node ID which is incrementally updated based on the row number. But then we also have to load some more users, and we have several other nodes as well. So we want our node ID to be unique. So what we do is we just select the node ID, the maximum node ID from the previous, you know, and we have to establish order over here from the previous model that we use. In this case it's the tracks one, because we are doing this in order. So for the tracks one we get the maximum node ID from the users one, from the SN, the one that we first looked at, and we just increment based on this baseline, and then we do it again for users, for this MSDSL dataset. And for genres we create a union from both the DSN datasets and the tags from MSDSL, which are now converted into title case. And this is pretty much how you can use DBT to you know, to create some SQL-based pipelines and power your data lake somehow. So in here we've got also tests for the nodes. For instance, we want to make sure that the country is one of these options, because we know there are only 3 countries. Let's see. For this we want to make sure that the source is MSDSL. I believe we also have some for edges as well, and these are a bit more useful in the sense that these tests make sure that when we are defining an edge, the node ID, the source ID or target ID match an existing node ID. This was extremely useful during the ETL, the transformation stage, because we were having errors when importing data into KùzuDB. or rather when trying to run some computation over it. And this having unique node IDs simplify the process, and in order for us to make sure that these IDs are really unique and exist and are, you know, linking to actual nodes, we have this test over here. And speaking of tests, let me show you how you can run these tests. So if we go into here and we run, I believe it's a test, this will call dbt test essentially. So it's just a wrapper to inject the environment variables that it needs, and hopefully all the tests still pass. And keep in mind, these are data tests, not unit tests or integration tests or whatever. So these are extremely useful for data engineers. You have to make sure that the data that you transform is output as expected, and implementing these tests will help you make sure this is the case. And as you can see, all the tests pass, and if you clone the repo, you can, you know, look into more detail on how this was implemented. So we can also implement, besides these generic tests or the ones that are already bundled, or even the ones you can find in dbt utils, which is a package that's installed over here. Besides these, you can also implement your own tests for more complex queries. So in this case, we wanted to make sure there were no duplicate IDs, no duplicate node IDs, they were unique across all node types. So we just implemented this. If it returns something, then the test fails, so it should return nothing. As you can see, we just select all node IDs, we group by node ID, and if any of these has a count that is larger than 1, it means we have duplicates, and so this query will return records. And this is pretty much how you transform your data using DuckDB, DuckLake and dbt. Some other interesting details include, for instance, as I was saying, there is documentation, and dbt can generate a really nice UI for this documentation. So we have this docs will run the docs command on dbt, and you can either generate the docs or you can serve the docs directly, and we are going to first generate and then just serve them directly, and we'll go through it. So it is available on localhost. Let's switch to the browser, and as you can see, this is what it generates. There is a transform project, which is our project, and then there is documentation about everything that we added, and specifically our models. This is perhaps the most interesting one, and in here you'll find all the documentation that you added for each column, and all the references, all the dependencies, and even the code. So this is a really nice way to provide information to your data science team, for instance, if you are the data engineer. So now that you have your data lake created, you can also just use the generate init SQL tool. This will create an init SQL file under your local directory, which looks something like this. It will contain your min.io or S3 secrets over here, so this is why it's not pre-created, and it will also contain the full paths for your catalog databases. And using just DuckDB init local, you can just this you can run it in memory directly, or you can use the actual engine database. And if you go into here, you'll see that all your all your loaded data plus the metadata tables are listed here. So for instance, if we want to look at some data from the stage intermediate process, we can look for instance at the edges over here, or we can look at the genres over here, and we can also look at the final data from the graph smart, which is the music taste graph, and we have a bunch of nodes over here, for instance the genres nodes. As you can see, there is a node ID that is unique, and there is a genre that is now in the form of a string instead of an array. We also have some specific nodes to each dataset, so something like this. And that's pretty much it. You can also back up your catalog, so ctl backup. In here, this is just a fancy copy of your files into a bucket, but you can just create a backup like this. And now if you go into the min.io instance, you'll find there is a backups directory, and in here you'll find your engine, your stage catalog, and all your marts. You can list the backups like this, so you run ls and it will output the date for the backup as well as the path. You can also check all the files that you have in a given backup. This is not the default, just because when you have lots of backups with multiple marts, this will be quite extensive. And then you can restore a backup, either just restore the latest version like this, it's the latest version you need. Maybe you switched from your laptop to another machine and want to continue your work, or you can just download a specific version into a temporary directory, something like this, and this will be the latest version. And if you just ls this directory, you'll find your files. Or you can simply select one of the versions, and let's look at, we use the date for this, so let's look at the backups that we have, and we just use a source and paste the date that we want to restore, and this will restore this specific snapshot. Although keep in mind that this doesn't move any or restore any files within your data path, so it should still be compatible with the files that you have. Otherwise you'll start getting some errors when you query. Finally, in order to use any of this data, we can use the export command, and this will give us a readable output, so we can do something like graphs, which is one of our marts, music taste is one of our schemas. So if we run this will essentially just copy the latest version into a readable output. And if we go into min.io, we'll find a new directory called exports, graphs, music taste. There is versioning, and so for the latest version you'll find readable data over here, and this is the data that you should be using as the output of your Lakehouse. For instance, we are going to use this in the next video to load into KùzuDB directly, because KùzuDB supports Parquet, and we are going to load our nodes from each of these Parquet files, and load our edges from each of these Parquet files as well. Next time we'll dive into KùzuDB, importing the nodes and edges we prepared today. The goal is to build a knowledge graph that will support a graph RAG task for music discovery. So something very simple, just to demo the tech. You'll be able to find the companion blog post for this video as usual at datalabtechtv.com. You can also follow the channel on Blue Sky and join Discord to receive announcements and discuss topics like data science, data engineering or MLOps. I would love to have your questions or your comments or your knowledge over there. And don't forget to drop a like and subscribe for all things data as usual.